Ladies and gentlemen, welcome back for another round. This is Mr. Doolin, and I thank you for tuning in. Here we go. This is free energy. We're going to wrap it up. This is part 3, the final part. Hopefully you have made it through with your soul from the first 2. And you kind of understand. I guess first off, you should know that the Gibbs energy equation is delta G equals delta H minus T delta S. That we are going to use this equation to calculate an overall Gibbs energy value, and a negative Gibbs energy value means that something is going to be thermodynamically favorable or spontaneous. All right, and we want to make sure that you get the relationships in here as well, right? Because remember, the second law of thermodynamics is what the end-all be-all is for thermodynamic favorability, and it states that the entropy of the universe actually has to increase for something to be spontaneous, and Gibbs' energy equation actually uses this enthalpy of reaction value to, indirectly calculate the entropy value of the surroundings. And then I've got my entropy value here, and so really what we're doing is we're using Gibbs' energy equation to calculate that overall entropy change for the universe. All right? Okay, now that's conceptual. So what does actually delta G tell us besides thermodynamic favorability? All right? And man, I got to write it. Negative delta G equals favorable. Positive delta G equals not favorable. I need to write that down. Okay, so what does delta G tell us besides this thermodynamic favorability? Well, it tells us approximately how much work our reaction can actually do. Because the units are kilojoules per mole for delta G, it's really, right, because joules is an amount of energy, it's an amount that we can use to do work. It tells us approximately how much we've got. Now, it's not, I wouldn't say, like if I had a reaction, like I think the last one we calculated was negative 461 kilojoules per mole as my delta G value. We know it's thermodynamically favorable. This doesn't actually mean that I've got 461 kilojoules of energy to do work with, right? Because remember, some of this energy actually has to go into the surroundings to increase that entropy and make sure that the entropy of the universe is increasing, right? But what we need to understand is it's an approximate value that we can use to actually do some work with. And that's really where a lot of chemistry lies, is how do we use the reactions and the energy exchange and the reactions to our favor? How do we manipulate and how do we use that in everyday life? All right? Okay, so a couple of things. Let's run through with delta G and just tie all the loose ends. First off, what does delta G look like at equilibrium? Right? What does delta G look like at equilibrium? So remember a galvanic cell, right? At equilibrium, it was E cell equals to 0, and this is very similar. Delta G at equilibrium is equal to 0. All right? And so that's not a big stretch, because remember, if this is the ability, if delta G is telling us this ability to be able to do work, remember E cell at equilibrium was 0 because I've got a net transfer of electrons of 0. I've got electrons going both directions in the same rate, and so I don't have any net electron flow. I don't have any electrical energy to actually do anything with. Right? And so it should make sense, if we're relating our delta G and our E cell values, that delta G at equilibrium is also 0. My forward reaction, my reverse reaction are going at the same rate. I've got no net change in the system or in the overall reaction, and so I don't have anything to do any work with, okay? All right, now how is delta G related to equilibrium? This is going to complete our triangle, and it's delta G is equal to negative rat link, Rn natural, like the RT natural log of K. Now this is kind of a funky thing, because remember delta G needs to be in kilojoules per mole, right? If we use, and this is the gas constant, if we use the gas constant of 0.0821, that's liters dot mole Kelvin dot atm, or liters dot atm Kelvin dot mole, right? There's no joules units in that constant, and so there is actually an R value that is 8.314, and it is joules per mole dot Kelvin. And so that's the R value that we have to use in this particular situation because it's got that unit of joules, and it will actually give me the ability to calculate a kilojoules per mole for that, okay? All right, the next thing that we're going to take a look at is using our enthalpy, entropy, and Gibbs energy to predict favorability of a reaction. And so what I'm going to do is I'm actually going to put a table up here, right? I'm going to have delta G, delta H, delta S, and I'm going to pause the video and go ahead and draw everything in. Okay, and so I've got all the values drawn, and if you're looking at this, I'm just telling you positive versus negative for my delta H and my delta S values. Now, everything kind of plugs into, everything does plug in to Gibbs energy's equation, and so we're going to be able to predict when we're given particular values whether we're going to end up with something that's temperature dependent, always favorable, or never favorable, okay? So my first one, if this delta H is a positive value and delta S is a positive value, what I end up seeing is that this overall ends up being a negative value, right? After I change signs and everything else, it ends up being a negative value. So the bigger that part of the equation becomes, the more likely delta G is to be negative. And so what we say is that when I have both a positive H and a positive S, the reaction becomes favorable at high temperatures because it'll make this part of the equation larger. Okay, now the next situation that we're going to look at is when I have a positive H and a negative S. So in this particular case, this ends up becoming a positive value overall after I switch signs around. And so I got a positive and a positive added together. I can never have a negative. And so what we do is we say that this is never favorable. Never favorable, right? That'll never be a spontaneous reaction, all right? And then the opposite is true for the next situation where I end up with a negative and a positive over here. Well, this all ends up being negative, and so I've got a negative added with the negative, and so delta G can't be anything but negative. And so what we say is that is always favorable, right? And then in the last situation, I end up with a negative H and a negative delta S. So this ends up being a positive value overall, right? Because after I switch signs, and you should, if you don't understand these, ladies and gentlemen, reason this with yourself algebraically, all right? So what happens is the larger my temperature gets, the more positive this becomes, and as I increase in temperature, I become unfavorable. So what we say with this one is that this reaction or this situation is actually favorable at low temperatures, all right? And so those are my four situations, ladies and gentlemen, with my enthalpy and entropy values. So we need to understand these two right here are the easiest ones to remember, and then favorable at high temperature, low temperature. Those are a little bit trickier to get into, but make sure that you understand where we get them all from. Now, we do want to know or point out as well that there is a limitation to this delta G value. And I want to make sure that everybody understands this because I've been throwing out this word spontaneous, and I don't want you to infer or think that when I say reaction is spontaneous or if a reaction is thermodynamically favorable, that it happens quickly, right? That is the one limitation with our delta G and our prediction of spontaneity or thermodynamic favorability is we don't know how fast this is going to occur, all right? Like the degradation of a diamond into graphite, which is the same thing in your pencils, that's a thermodynamically favorable process, but it is like a billion years to happen, right? It takes a long time. It's a very slow process, okay? So please understand delta G infers nothing about how fast something happens. It just tells us whether it's favorable or not favorable, okay? All right. Hopefully you got all that down. You got some questions. If you have them, I'll see you in tutorials for those. And other than that, I will see you in class.